We are going to see on this lecture the application of the root locus method and understand a little bit more how it works and what it is. So on the screen you have a system that we can say this is your transfer function right here. Then you have a feedback loop in here. And having this basic system, we can obtain this transfer function in here. We're assuming in here you multiply k times g, which is the gain. If you have this kind of system, you can have this transfer function in here that we see right here. This is the you say the entire system is replaced by this transfer function of the whole system. So now we are going to study what happens to the roots of the characteristic equation of this, or so-called poles, the zeros, which would be the roots of the numerator, and how that influences what we're doing. So let's just close here. And then if you have a let's see, a pole here, you know that this will correspond to this kind of, this is the numerator. You know, this is called a zero, and this is a pole. So a pole is a root of the denominator, a zero is the root of the numerator of the transfer function. So here's a practical transfer function shown of a camera in this case. This camera automatically follows the subject who wears infrared sensors on their front and back. So this is would have also a microphone, so tracking commands, and audio are related to the cameraman. Okay, so here's what we have. You have the system, feedback, and then the amplifier here. This entire block diagram can be reduced to this transfer function. So if you make an evaluation, if you give, let's say, a value of k, this constant right here, if you give the value of 0, 5, 10, or so on, you will obtain the values of the poles in here. And so what I suggest we do is we keep like a statistical table of those values, and what you will have is you have this locus that goes like this, yeah? And you have for different values of the, depending on what the gain is, that this comes from this table, pole 1 and pole 2. In this case, you can actually go into MATLAB and obtain the transfer function of this. So what I did is, let me show you here. I think, well, right here. I think what we can do is we could depart a little bit from the PowerPoint and go into MATLAB and put this in. So I'm going to show you a nice way to do that. Perhaps it's in a slide a little farther down in here. So excuse me for, yeah, right there. So I modified this to make it easier for you here. What you have is Go to MATLAB and put this statement in here. And then we'll put the transfer function as you see up there. I think this is actually a very nice way of doing the transfer function. So, and I would say it's in a new way than what we have seen in the past. So why don't we keep this in there, and then we'll go into MATLAB and do this. So let's just keep it there. Oh, perhaps, yeah, there you go. And so now we need to go. Where's my MATLAB icon? So that way we will rearrange our windows in here. So let's do it together, okay? Just go to MATLAB. Okay, so you have in here. So here's what I recommend you do. Go and say S is equal to the transfer function, and then say S like this. What you have done is actually define S as a Laplace operator. In fact, transfer function of S, because any factor that you multiply by it would now produce a transfer function type expression. So what do you have up there? The first one that you have, it says S plus 3, right? So I am going to say G is equal to, put like this, S plus 3, like this. Yeah? Oh no. Then put plus, like this. And then close the parentheses. And then, no, it's multiplied by the S plus 4. So multiply by S plus 4 like that. And now we need to divide, but we need to divide the entire thing. See here? We better make sure that we do this right. So this divided, and the denominator also has an expression with two factors. So this is S plus 1, like that. And then multiplied by, there are other ways to enter this into MATLAB, but I find this personally for me is the easiest way. And so I'm passing it along to you. So if I do this, what happened? And I have a little mistake in there. One parenthesis is wrong, and I believe I am missing one in here. Well, I mean, professors are not perfect, so you're always supposed to make mistakes too. But here is the transfer function. Now, what I would do is I say G, our locus of the transfer function, G, did we say G1 or G, right? G was that G? And so it goes and thinks out for a little bit, and it should come up with, there you go. You see, so this is your, so let's discuss this a little bit based on what the author is saying. Perhaps a good idea would be to just have two screens in here. Yeah, why don't we do that? And then now that we put this up in here. Okay. We cannot have it in half, huh? Well, maybe. It's a good idea to have it like this. So you see in here, the poles are at -2 and -1. You see what happens right there? -1, you have -2. Huh? And then you have these zeros at -3 and -4. So -3 and -4. So you see how MATLAB also keeps the same notation, the little x's they put in here, and then the zeros over here. Huh? And then you have this. Yeah. So what the author of your book has done is to study in detail the influence of the zeros and the influence of the poles. And what he's saying is that you could draw these vectors here and plot them in here, and in his case he has it like a perfect circle here, you know. But that's the idea here. And then what I did is I put it all together in here so you can see. But we need to study several of these. Like for example, this one. You know, this is a different transfer function. In fact, I would like us to give it a try to this as well. Can we give it a shot here? Because you see, now you have like 4 terms on the denominator, and you have 1 in the numerator. What does it do? So I am going to define as G1 equal to what? Do you see how it is? The numerator is s plus 3, like that. And then the denominator is going to be s times, not pound, but this symbol. And then you have, this would be s plus 1. Plus 1. And then you have star like this. And then s plus 2. And then the star over there. And then you have a final one, which would be s plus 4. Plus 4. And then we close the parentheses. And we say, okay, look, this is the new transfer function. And if I do R locus of the transfer function G1, I should get a new plot. But this new plot is very interesting because this is going to show you what unstable, what's happening. I think we need to close this one so the new one will appear. What did I do?
You just closed MATLAB.
I closed MATLAB. But anyway, here let's just use this. This is what you will get. But do you see what happens in here? Right there and here, the system no longer is stable. So what we are going to do is to play around with the position of the poles to change the gain, to change the response, to do all kinds of things like that. Okay, so we'll stop here.